Good morning, everyone. I hope you're enjoying our nice spring weather. I think that it's been very nice over the weekend, and we've enjoyed less rain, and so I'm grateful for that. The pollen, like said last week, I don't think is as bad as it was last year, but maybe it's just in my imagination. But I sent out the Blackboard announcement in the email about the test that we have this week. And so again, and I've had a couple of questions about the coverage. Remember what I said last week is that we will cover through section 6.4. I've already covered law of signs, but I'm not going to include that on this test. I could, but I've decided just to stop the material at 6.4. Now, that doesn't mean as you do practice material and stuff, you may see the law of signs, and you are certainly encouraged to go ahead and work through it. But like I said in lecture, the material will stop with 6.4. So again, if you look at the announcement, then it's clearly stated there. So there is no need for clarification if you listen to me. So be responsible college students and listen to what I say. I'm trying to give you the right direction so that you can have the success that you want. Of course, if you put in the time, and that's always the little issue that we all are contending with, trying to balance our time to make sure that we give a STEM mathematics course sufficient time. As I've said to many of you in conference hours, your STEM math course should always be a priority. It will never be a class that will be easy. It will always offer challenges and keep you busy. And of course, being a STEM major, it is the cornerstone of what you will be doing, regardless of the field that you initially or that you ultimately choose. I know a lot of you find yourself trying to say, well, everyone comes up to you and says, well, what do you want to be? And so you say, oh, well, engineer, doctor, dentist. I mean, we say these things when we're younger because it's like, okay, well, I've got to say something so I don't get, barraged by all these questions. And so as you continue to evolve as students and you gain experiences as you speak with other people and you investigate things, you're gonna really determine what it is you like to do. And that is not an easy decision. So just know, however, that whatever STEM field that you do pick, math will be an incredibly important component of it. And so you don't have to worry about the fact that you may not have zeroed in on what you want to do, but certainly the mathematics is something that will always be there. And so spend the time on it and enjoy the rewards of your hard work. Now, what we want to do today is to talk about the law of cosines and then talk about just some preliminary uh, identities. You already know the first section of chapter 7. It's basically review, but we set forth the idea of taking an equation and verifying it. We already have plenty of equations that we're using in trig that we rely upon. They are fundamental in the sense that the identities secure us in the study of trigonometry. Now, of course, there are tons of identities, some that we'll never use again after we verify them. But the ones that tend to come up the most, we will focus on in this class, especially in chapter 7, because when you take calculus, there are particular trig identities that come up quite often. And I will tell you this, ladies and gentlemen, those will be the ones that you'll keep up here because you use them a lot. We're all creatures of habit. If we use a particular construct on a regular basis, we learn it. We might think, well, we memorized it. Well, there's a little bit of difference between that. If you use something often, you basically master it. If you're taking a government test, you might be memorizing terms that you don't fully understand, but you have a good short-term memory to be able to throw it back. But then, of course, as time transpires and all. You've got to go back and put everything together just like you do in math. So you know, we love the fact that we can stuff things up here for, you know, a short amount of time, but the long-term knowledge is what is difficult, and we have to synthesize connections between items so that we remember them. And boy, I guess if we had a magic wand, we would make that easier. Okay, so let's go ahead and get started with our law of cosines. Again, I will do some justifications today, but I want to again give you some ideas of how you can actually do this and use it in solving problems. You will use law of cosines and law of sines in physics, maybe not so much in calculus, but they are certainly components of engineering problems. So that's why we cover this, even though, like I say, you'll probably spend more time with the topics in chapter 7, but that's fine. Now, we had two cases that the law of sines really could not get us started. That is, if we were only using the law of sines, we could not push forward the solving of the triangle. And these are the last cases. We have side, angle, side, and side, side, side. Now, these are determined cases. It's not like the ambiguous case where we have side, side, angle, and we're like, okay, well, what's the sine equation going to tell us? Well, maybe we get no triangle, maybe we get one, maybe we get two. With these types of hypotheses, we can again get zero, that is, it's not constructible, or at most one triangle. So we don't have to worry about an equation that's going to give us another solution that could possibly create another triangle for us. So in this case, we need the new theorem. Now, this doesn't mean that this is the only theorem that you will use, and I'm referring to the law of cosines. After that, then you can use the law of sines, or you can use whatever you want. It's just that if we want to get the ball rolling, the law of sines will not help us here. So we need the new theorem, and the new theorem is the law of cosines. Now, you may have already seen this before in a previous class. Maybe you've seen this in a physics class. If you haven't, it doesn't matter. We sometimes call this a generalization of the Pythagorean theorem because it extends the Pythagorean theorem. So we can say extension of Pythagorean theorem. We need it to justify it. That is, we have right triangles when we justify this theorem, but what we're finding is that the justification basically is extending the Pythagorean theorem that we use in the actual proof. So that's an interesting topic there. You know, we use a theorem that we rely upon, but then when we study the equation, we see, oh, that's just an extension. So what we do is we start with the standard triangle. So consider, and we have our lazy generic triangle. Consider the generic triangle. Again, we have the A, the B, the C, and the D. And then, excuse me, the A, the B, and the C, and then the lowercase letters opposite the uppercase letters for the lengths of the sides. So it's a very quick way to do it and a very lazy way to do it, but we are glad to have it. Then, and this has three equivalent forms. I'll just write all three of them down. A squared equals B squared plus C squared. Now that's starting to look Pythagorean, and then we have this correction factor, 2BC cosine A. So again, all of these letters here denote lengths of sides, and the only angle here is A. So that's where we get the law of cosines. Now you can already look at this. If A were pi over 2, then this term would be 0, and we would just be left with the standard Pythagorean theorem. So this is what we call by an extension of that result. And then, of course, we can just move everything around. Maybe we have B squared equals A squared plus C squared. And then the correction factor, 2AC cosine of the opposite angle of lowercase b. So one way to remember this is just remember that the b and the c here are then repeated in this correction term. And then, of course, the angle that we use is the one opposite this term. So that makes it really simple to remember this. And then, of course, the one that we like, that we normally write the Pythagorean theorem, we say c squared equals a squared plus b squared. That's the normal use of letters for the Pythagorean theorem. I think you probably learned that in the 5th grade. And then, of course, you have the correction factor 2ab cosine c. So again, when you justify this, you don't have to do all three because you're just moving the letters around and you're just focusing on one angle as opposed to another, and that is all symmetric. So like the law of sines, there's certain characteristics about this theorem that are very useful. But what you can see here is that if you had like side angle side, you'd have two sides here that you could just go ahead and fill in. And you have an angle here that you would have, and then you could solve for the remaining side here. And then after that, you can use your law of sines if you like. If you have side, 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 then you think you've got the A, the B, and the C, and you can solve for the angle. So this is a different construct from the law of sines. The law of sines needs two angles and a side, or two sides and an angle, but they've got to be in the opposite configuration. And if you don't have that, like you have in these two cases, the law of sines is not helpful. And you don't even have to memorize it, really. You just kind of look at it. And a lot of times, if I give you a hypothesis, we'll draw a triangle that kind of mimics what we have and then look at the geometry. Now, the justification is pretty simple. But what I want to do is an example. Then we'll go back and we'll show maybe one of the cases as to why this is true. I think you'll enjoy that. And it's a good exercise using trigonometry. Now, one other thing that we're going to get from this is an area of a triangle, which may be something that just blows your mind. It's called Heron's formula. You may have seen that before. And it's a remarkable result that we start with our nice new area formula using the sine, and then we morph that into a different type of problem using the cosine law, and then again produce an actual area formula that only uses the side lengths. And so that is an amazing result. And then, of course, Heron was a Greek. And of course, they figure all this stuff out by geometric means. And now, of course, we're lazy and we use analytic geometry and algebra because we're not that gifted. I mean, the Greeks were very, very creative, and we are certainly indebted to them for their mastery of education. That again, we put it right on our shoulder and we use it. So let's look at an example of this. So what I have here, and again, I've got all these nice justifications. The proofs are good, but I want you to see this in action so you can kind of think about what we did with the law of sines. So here's an example to get things rolling. Say we have some side lengths. B is 60. Again, somewhat unfortunate sizes, but I'm just using this because this is good practice. C, or the side length C, is 30. And then the angle A, of course, is 70 degrees. Now remember, in all of this, as we use our Google calculator, we use degree mode. So we do not have to do the conversion from radian to degree. And this is very useful. This is one of our nice perks of using the degree mode in doing these problems. So certainly always remember that as you get your approximations. Now, what I want to do is just make a little drawing here. It's not going to be, you know, an art piece of artwork, but let's just do a little drawing. And of course, this is not to scale. So I'm going to put my A here, and this is going to be 70 degrees. And then I'll just mark C here. So here's lowercase c and B here. and here's lowercase b. And of course, you can do this in any configuration you like. Doesn't matter. It's not going to change the result. And b here is 60. C is 30. And I've already marked in the fact that A is 70. So this basically gives us a side angle side. So we can look at this and say, this is side angle side. So you don't have to just stare at the hypothesis and say, I don't know which one to use. That's not necessary at all. You can look at this and just draw a figure to get everything oriented. Use the generic triangle and then say, well, I've got this angle here, but I don't have the side opposite the angle. So I can't use the law of sines. So that's where we have to use the law of cosines. So now when we look at this, we've got, like I said before, we've got these two sides and this angle, so we can actually find little a. So in this case, we'll just say A is what we're interested in. So this is where we start with the law of sines. So this implies, to get the ball rolling, that we have a squared equals b squared plus c squared minus 2bc cosine A. So when you get all these rolling, just write down the theorem, law of cosines. And then we can fill things in. Now notice, and this is very important, if you will, let's just go ahead and see if we can just figure out what this side is. And then as we get to it, maybe more simplified, we can apply the square root. So we don't want to drag out the square root and write the square root 10 times and get a sore hand from all that writing. We want to just make sure that we simplify this side and then apply the square root. So to find A, ladies and gentlemen, we would have to take the principal square root. The negative, of course, square root would not be of any use to us. So let's just go ahead and fill this in. So this part, let's fill it in. So this equals, so we've got a 60 squared, and we'll try to factor things to simplify things as much as we can. And then we have a 30 squared. Then we have a minus 2. And then we have the b, which is 60. And then we have the c, which is 30. Again, I've used these kind of unfortunate numbers as a good practice problem. And then, of course, we have cosine of 70 degrees. Now, of course, that's not on the unit circle. So when we actually summarize things, we'll take our exact responses and approximate them using Google in the degree mode. So now what I've noticed here, we've got a bunch of tens in things. So let's go ahead and factor. So we're going to say 6 times 10 squared plus 3 times 10 squared. At least get the ball rolling and then make the numbers smaller. Look for some perfect squares. 10 squared is certainly a perfect square. Minus 2, and then we'll have 6 times 10 and 3 times 10. Sometimes the numbers won't be, any good for us, and we just work with what we have. So that's fine, but we see some common factors here. So now notice we've got a 10 squared here, a 10 squared here, and a 10 times 10, a 10 squared here. So let's go ahead and factor that from all of these terms. So we have 10 squared. And now, of course, that leaves us with a 6 squared, which is a 36. And then if you notice here, we'll have a 3 squared left over. So that's plus a 9. And then over here, notice we've got the 2, we've got the 6, and we've got the 3. So I'll just say minus 2 times 18. And then we have the cosine of 70 degrees. Now with this, what we want to do is see if we can get even some more common factors out of this. So we've got 10 squared. And notice here we've got a bunch of 3s in things, but it's not going to hurt anything to go ahead and add this together. So we'll get a 45. So 6 plus 9, that'll give us a 45 when we carry the 1. And then, of course, here we have a 36. So let's write this in a way let's just say in this particular case, we've got a 3 here. So I'll just say this is 3 times 6. And so that'll be a 12 times 3. Just to make that a little bit simpler. Now, one thing that's interesting here that I could even improve upon this, let's just see this. 18 is actually 2 times a 9. I just noticed that we've got a 9 in this. So let's write it this way. Let's just say that we have, in this case, a 4 times a 9, because this is just a 9 times a 5. So that's even easier. Cosine 70 degrees. So now we see we've got the 9 and the 9 here. That's a 3 squared. So we have 10 squared times 3 squared. And that leaves us with a 5 minus a 4 cosine of 70 degrees. Now that's really simple, or at least when we look at this, we see, okay, this is much more simplified than all of these numbers mashed together. So now we can apply the principal square root. Of course, we can easily take the square root of this. So this implies that a is the principal square root. And let me just use the bracket with the 1/2 to make it a little bit easier to write. So again, notice here, I'll go ahead and before I do my bracket, here we've got a 10 times a 3, so that's a 30. And then we have the bracket 5 minus 4 cosine 70 degrees to the 1/2. So this gives us A exactly. Now, again, let me just rephrase what we've done here. We have a new theorem that allows us to deal with side angle side. So don't guess, draw your little generic triangle, see how things are configured. We have side angle side. Then fill in the, again, based upon the letters that you've used, fill in the corresponding law of cosines. And then say, okay, well, we're going to solve for A by taking a principal square root, reduce it as much as you can, make it as simple as you can, because then you can deal with it in a much simpler fashion. Now, at this point, we're thinking, okay, well, what do we have here? Notice we've got an angle that's opposite, a side that's opposite angle A. So now we can figure out one of the other angles using the law of sine. So if you like, let's go ahead and figure out what C is. So for the next step, I'm going to say determine, just write down what you're going to do. You know, maybe when you do your test, you could be a little more clear as to what you're doing and make it easier for me to just check your work off. And I think that would be nice. So determine C with the law of sines. Okay, let's write down the equation. So we have sine of C divided by lowercase c equals, now we've got lowercase a, so sine of A divided by lowercase a. And of course, now we need to solve for C, the angle C, so we can just isolate sine C. So if and only if sine C equals lowercase c times sine A divided by lowercase a. Now, when I write all of this down, ladies and gentlemen, basically what I'm trying to do is just say, okay, before you start substituting numbers and you're not really sure what you're using, write down the equation and make sure that it corresponds to exactly what you need. And then what we can do is go ahead and substitute the numbers and take the inverse sign. So now equivalently, C will be the inverse sine. And again, what's Professor Ron going to do? He's going to write degree mode, okay? That way we don't have to worry about the conversion. That's one luxury of our Google calculator. So C is the inverse sine, and we can fill all of this in. So we have C, which is 30, We have A, which is 70, so we have sine of 70 degrees. And then A is right there. So just go ahead and fill it in. So we have 30, and we have 5 minus 4 cosine 70 degrees. Let me have room for my degree to the 1/2. So when you look at this and you think about what it is we're doing, we're like, wow, look at this. These 30s absorb. So absorb. How nice. So we have inverse sine of 70 degrees, make it as simple as possible, divided by the square root. So I'll use the 1/2 now, but of course, when we use our Google, we've got that square root symbol that we can use. And that's actually easier, but I'm just trying to do this now so you can actually see the square root and it's clear to you. You can use your square root symbol if you like. So now we have a nice, and I'll just say this, let me just put the C here so I can put a box around this. So we have the angle C, and we're basically determined. Basically what we see with the triangles, we get 3 pieces. We get 3 pieces of the 6, and the 3 will get the ball rolling, okay? Especially if it's a generic triangle. If it's not a right triangle, we love right triangles. Those are easy, but we need 3 pieces, and then we can move the process forward to solve the triangle. So now you can say, all right, well, B will just be 180 degrees minus the measures of A and C. So let's go ahead and write this down. So this implies B will be 180 degrees minus 70 degrees, that's A, minus C, inverse sine of 70 degrees. And then we have 5 minus 4 cosine 70 degrees to the 1/2. Now, of course, we can just do this subtraction. That gives us 110. So 110 degrees minus the inverse sine, again in degree mode, of sine of 70 degrees divided by the square root of 5 minus 4 times the cosine of 70 degrees, close. So here is B. So we have all of the ingredients here. Now, of course, when you're doing these types of problems, if a lot of you have, some fancy calculators where you can store values and things, and that's always a good thing to have, and certainly very useful. But when you're showing me your work, it's certainly a lot more convincing if I just see the formulation here. And again, I know that you can't be as precise as Professor Ron. I know that's not going to be possible, but I do know that you can show me your detail. And that's what I want to see. I'm not going to keep you so busy with calculations that your mind starts to blow up. I want to just be able to see your logical reasoning. Because if it just gets all chicken scratch and there's a little bit here and a little bit there, it's hard to pull it together. So one thing about these triangle problems, ladies and gentlemen, is that they kind of bring all of the ideas together. So academically, it's actually a good exercise, even though, like I said before, I'm not the biggest fan of these types of problems. They still do have an educational value. And of course, when you take engineering classes and physics classes, they're good. So now what we can do is a summary. Now, what we can do and what's usually customary is we want a 1 decimal approximation. 1 decimal approximation. And you all are good with this. 1 decimal approximation. So we're going to have a space for little a, lowercase a. We're going to have a space for, what do we have? C. And then we're going to have a space for B. Now, of course, you don't have to write the other given down. You could, but it's not necessary. This is the new stuff, and this is what we don't know. So let's go ahead and use our Google. Now, let me find my Google calculator. So Google Scientific, and let me move it down here. Let's see here. And so usually if I move it around, the Zoom can find it. So stop share. There it is. So here's Google. So again, remember, we want to highlight the degree mode, okay? The degree mode. So the first thing we're going to do is A. So we're going to have 30 times, and then we'll do the square root, okay? Then we're going to do 5 minus 4 times the cosine of 70 degrees. So cosine 70 degrees. Close and then close the square root. And in this case, this will give us 57.2 if we round to 1 decimal. Again, we just want to make sure that we're either keeping many decimals stored in the calculator, or we're keeping an exact expression and we only round once, okay? And that's the key to getting a good approximation, where you eliminate the round off error. And I know sometimes this makes you absolutely crazy, but you can't use numbers in your calculations that are severely rounded. Run things out enough so that again, as you're calculating, if you lose a little bit of time on a quiz, you're at least allowing yourself to avoid the unnecessary round off error. So now the next thing we need, and of course, if you think about this, this is something you could store in your calculator and then use again. That would certainly be permissible. I have no problem with that if you have that option. So now for the next one, we need C. Now look at your work that we just computed. We're going to use the inverse sine. So we're going to say inverse sine. And remember, that's going to also be notated arc sine. The Google calculator uses arc sine. So now we'll have sine of 70 degrees. And then we're going to divide by A. So we've got the square root of 5 minus 4 times the sine, or in this case, the, let's see, what did I do before? Let's see, I've got cosine, oh yeah, cosine of 70 degrees. Now I hope I used cosine the last time. I'll check that. I think I did. Cosine of 70 degrees. I didn't. I'll have to go back and fix it. Okay, so we close that. Let's see what we get. So we get, in this case, 29.5 degrees. So very good. The idea here is that when we look at what we do and when we look at how we compute things, we want to make sure that we always have the degree mode in check. Now for the last one, again, you can store this if you want, but I'll go ahead and write it out in a character string. For B, look at your notes. We have 110 degrees minus the same thing that we just computed, and this will be good practice. So we have 110 degrees minus inverse sine. So look for the arc sine. So we have sine of 70 degrees divided by, again, our square root again, square root. So we have 5 minus 4, and we have the cosine of 70 degrees. We close that out, and we close out the square root and then close out the arc sine. And we get 80.5 to 1 decimal degrees. So again, when we go back to our summary here, we now have one decimal approximations from our exact calculation. So we have an exact expression for A, which is this. We have an exact expression for C, which is this angle here. And we have an exact expression for B, which is this angle here. And so again, what's important is that we organize our work, just like we did with law of sines. It doesn't mean that everything has to be ultimately precise, just so long as you have some expression that you can enter into the calculator to get the one decimal approximation. Otherwise, ladies and gentlemen, we'd be using tables. And tables are fine, but you all don't use slide rules because you didn't grow up with slide rules. And the thing is, slide rules were starting to be phased out when I was in high school. And so that's when the calculators started coming around, and we thought we were special, but we really didn't use them because they just weren't that effective. But the idea is that we can use our Google calculator to get some really, really nice calculus approximations to complete the exercise. So this is a very nice problem. Now what I want to do is another example where we have side, 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 okay? And you're thinking, well, you know, that's not very interesting, is it? So I thought, you know, if I want to do something useful in this lecture today, I want to give you plenty of examples. So we have A equals 10, B equals 12, and C equals 16. And we want to solve the triangle. So when you think of solving the triangle here, you can, I mean, there's nothing to, you don't even really need a picture, but let's just go ahead and draw one. You know, again, just our generic triangle. Again, not necessarily the scale. We'll make this side 16 since it looks like the longest. And then we'll say B equals 12, and we'll say A equals 10. So now, again, we've got what? A here, we have B here, and then of course we have C here. Now, this is called side, side, side. And now, of course, you know that the law of sines won't work. In the previous case, if you actually drew the triangle, you could see, well, I don't have an angle opposite a side. So that's where the law of sines will fall apart. And then we have to use the law of cosines. Now here, we're like, okay, we don't have any choice. So what I would suggest here, we can do the same thing we did before. We've got the A, the B, and the C, and just use the same equation. So we'll use the law of sines to get the ball rolling. So now what you see, ladies and gentlemen, in this particular case, we solve for two angles, and then we can get the third with the degree sum. So again, this gets the ball rolling with the law of sines, law of cosines, and then we can go to the law of sines to get the other angle and then move on to the third one. So again, we can say A squared equals B squared plus C squared, just to pick on that first one. No, you know, I'll show you another way that we can use these configurations, minus 2BC cosine A. Now, one thing that is actually kind of useful here, we don't want to spend a lot of time dragging the inverse cosine through all of our calculations. Like before, we don't want to drag the square root through the calculation. So we're going to try to simplify first, maybe get a nice number to make our calculation formulas a little bit simpler. So what we can do, and this is a quick way to do it, is transpose. We're going to take this over, and of course, we're going to take this over. So basically, the signs will just interchange. And then we can solve for cosine A and reduce that. So equivalently, we'll get cosine A. Remember, it's already over on this side multiplied by 2BC. And I'll show you a trick here. We got B squared plus C squared minus A squared. So we took the A squared over in the cosine term, but of course, that we've got the 2BC here, which we can now just divide 2BC. And so this gives us the equation for the cosine of A. So again, the intermediate step was 2BC cosine A equals B squared plus C squared minus A squared. That's just flipping them around like I did here. And then you divide by 2BC, boom, right there. There's the cosine of A. So if you use the formulas in an algebraic way, then you can really organize your work. And this is really good for you all that think that you might eventually one day want to become a grad student and be a teaching assistant, or maybe be a physics professor or something. Practice teaching these. Find some interesting students who don't understand this and practice teaching this to them and show them some nice techniques. You know, it's a good way to practice your skill sets. So now what we can do, just like we did before, let's go ahead and fill in these numbers and simplify this expression and then apply the inverse cosine. So again, we have B squared. So we've got these unfortunate numbers again, 12 squared plus C squared. So we have 16 squared minus A squared, 10 squared. And then of course we have 2 times 12 times 16. Now, what I would say in this case is just to do the same thing we did before. We've got some common factors here that we can try to factor and absorb from what's in the denominators, because we've got some even powers or even factors here, which we certainly have upstairs. So let's do the same thing, just very simple techniques. So we'll say, of course, we've got a 2 in every one of these. So we're going to say 2 times a 6 plus, in this case, we've got a 2 times an 8, and then we have a 2 times a 5. So just some basic factorization. We know we have a 2 in each of these. And so when we actually factor the 2 squared, that'll give us a 4. So let's go ahead and pull out a 4 out of this. We've got the 4 right there. So we're going to say 4, and then in the brackets, we'll have 2 times 12 times 4. So we'll just pull the 2 and the 12 over and take a 4 out of the 16 and write it here to just refactor. And now the 4 will absorb with the 4s upstairs. So if you like, let's go ahead and write this out. So this will be a 4, which we factor here, and that'll leave us behind with a 6 squared, which is 36. And then, of course, we have the 2 squared, which is 4. That leaves us behind with an 8 squared, which is a 64. And then, of course, we have the 2 squared here that we factor. That's the 4, and that leaves behind a 5 squared. So we have minus 25. So those numbers are simple. And then, of course, downstairs, we have the 4. And now if we look at this, we've just got what? We've got a 24 times a 4. So if we want to write that, 24 times a 4, the 4s absorb. But now look how neat the numerator is. That's just a 100 right there, 36 plus 64, and 100 minus 25 is a 75. So we're getting some nice numbers. And then of course here we've got a 24 times a 4. So take a little bit of time to reduce this. And of course, now you can see if we look at a factorization here, that's a 3 times a 25, right? So 3 times a 25, and we've got a 3 downstairs clearly. So we have a 3 times an 8 times a 4. And of course, the 3's absorb. Use this technique when you want, or don't write anything. Certainly don't put slash lines. You can put boxes or checks. Really, ideally, you don't even need to put anything, just align things so you can see that they absorb. That's really how technical writing is done. And as a STEM professional, you will do lots of technical writing. Slash lines will be forbidden. So get unused to that if you're still doing it. And on their next test, I don't want to see any. So now we've got what? 25 divided by 32. Now, of course, the idea here is this number is a whole lot more simple than this mess of numbers. And it's reduced at least in terms of least common denominator here, for instance, we look for the greatest common factor between these two numbers, it is indeed 1. So now we can apply the inverse cosine. So if and only if A is the inverse cosine of 25 divided by 32. Now again, degree mode. This is really important. The degree mode. We can always make our conversion change, but you have enough to deal with this problem. I think that that's a fair exchange. Use your degree mode. Again, if you want, you can just put a little circle there in degrees. Again, we can rely upon the fact that the Google calculator has this mode that will do the conversion for us. It will multiply by the 180 degrees divided by pi to give us the degree measure. So that's a very nice luxury that we're using. Now, again, we'll just pick something here. Let's just say determine what we've got A, so let's determine B. Same song and dance. So we'll say sine of B divided by the lowercase b. And if you like, we figured out what's going on with A, so we need to use that clearly. Sine of A. So we get to use our composition of a trig function with an inverse trig. You know how to do that, but let's blast from the past, right? A. So now we need B, so we'll multiply by lowercase b. So sine B equals lowercase b times sine A divided by A. So this is a nice little algebraic journey. Nothing difficult, just follow the basic algebra. So now we've got this, so we're good to go. We've got what? B is 12. So we have 12 times sine of A, which is inverse cosine of 25 divided by 32. And then A is 10. So now this gives us, if and only if, sine B, and of course the 2's will absorb here, so we get 6 inverse sine of inverse cosine. I'll go ahead and put the parentheses here. The Google calculator puts them in, so, and your WebAssign does the same thing. That's fine. Divided by 5. So now we've reduced this just like we did up here, and so now we can apply the inverse sine. If and only if B is now the inverse sine, arc sine, if you will, of 6 sine cosine inverse. Here, let me move this 10 up and to the side so it doesn't get in the way. I'll write it kind of small, put the 10 there. That way it's out of the way, doesn't get confusing. And then we have our 5. So now, again, we have a nice formula for B. And now we can write down C. So this implies, and then we can use our Google calculator. So this is not a hard exercise. It's just an exercise in using good mathematical skills, okay? So again, this is just good practice. This is good training, good teaching problems for you future professors and graduate assistants. So now we get 180 degrees minus A and then minus C or minus B. So if you will, we'll go ahead and put A. So all in degree mode, inverse cosine, 25 over 32. And of course you can use your storage capabilities, or get clever with the Google calculator. Then minus B, which will be inverse sine, all in degree mode, 6 sine of inverse cosine of 25 over 32 divided by 5, all in degree mode. So we've got all these nice formulas. So again, like I said before, if you look at what we have here, if you want to store these values, if you've got a calculator that has storage capabilities that will run these out to many, many decimals, that's always certainly a possibility. But it's not required. Hannah just takes a little bit more time to enter these, but that's certainly something you can do. Or you could write them down, but if you write them down, it's hard not to make a careless mistake and then ruin the calculation. So now we need a summary. So in the summary, what we'll do, ladies and gentlemen, let me write that so you can read it. We'll go 1 decimal. So summary, and I'll put this in red. We'll do a 1 decimal approximation. 1 decimal approximation. Now, maybe you're working with some clients that want more, but maybe that's about all the instruments they're using can muster. We want to have nice, exact computations here so that we can supply our client with whatever they need. So now we have A. Let's see A here. We can go ahead and compute that. So let's go. We've got all of our equations here in degree mode. So let's go to our Google. I know you all can use a calculator, but I want to make sure that you are aware of the Google. So now again, degree mode. So for A, we have inverse cosine. So that's arc cosine, 25 divided by 32. I think everybody likes this because this is devoid of a lot of theory. So in this case, to 1 decimal, that'll be 38.6 degrees. How nice. And now B, we have a nice formula for that. So B, we have inverse sine. So make sure you see arc sine. Nice thing about the Google is that you've got this beautiful printout and you know exactly what you're typing. And if you make a mistake, you can read it and say, well, I messed that up. And again, this at least gives you something you can see. So with the B, we're going to have what? 6 times sine. Now we're going to apply the inverse cosine. And then we'll have 25 divided by 32. Now we want to close out everything except the inverse sine and then divide that by 5. So close out the inverse cosine and the sine. Then we want to divide by 5 and then close out the arc sine or inverse sine. And that gives us 48.5 degrees. All right, and so now do not use rounded numbers to compute the third angle. Don't do it. You get all kinds of mess. So now just for practice, we'll say C, and we can write this out. C will now be 180 degrees. No approximations. You could store these minus inverse cosine, arc cosine, 25 divided by 32. Okay, minus, and now we'll do our inverse sine, look for arc sine. So we have 6 times sine of the inverse cosine, arc cosine, 25 divided by 32, 25 divided by 32. I want to close out the inverse cosine and the sine, and then of course divide by 5. Division by 5 and close that out. And that gives us 92.9 degrees. So again, the Google calculator gives us excellent 1-level approximations. That is, we get our calculations, our formulas, and then we go to the Google and we use our degree mode and we get beautiful, beautiful approximations. And that's what we're interested in. how do you know where you should use cosine or sine? Well, well, I mean, if we're using the law of cosine, well, you know, because of the formula. We use the law of cosines and the law of sines, and the formulas tell us what we have. There's no guesswork. There's no guesswork. It's based on the formula we use. You don't have to pick it. It's part of the formula. So again, when we use the law of cosines, obviously, we're going to, again, we, and your question might be saying, which rule do you use? Do you use law of sines or law of cosines? Well, you draw your triangle and see what you have. If you've got side, 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 the law of sines clearly will not get you started. So you have to use the law of cosines. And I think I've established that very well. So some of you may have to go back through these lectures and reassess. From some of your messages on WebAssign, it's very apparent that some of you are still struggling with just the sides of the triangles. So be careful that you get the major good. I like, oh, okay, I got it. See, I love that. That's what I want to hear. I'm like the boss that says, I want everybody to be happy. So work really, 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 really hard, and everybody, gets where they need to go. So just make sure that as you're preparing for this test, this is not going to be on the test, but ladies and gentlemen, if you can do these exercises, you're ready for the test. You're ready for the test. You can see why I want to give you a little bit more time to have this kind of settle in your brain, all right? But again, what we want to do is make sure we have some nice formulas to be able to use our one level of approximation. And again, those of you that have your nice storage calculators where you can store a decimal, it's got plenty of places and all that, that's also a luxury to save you a little entering time. That's fine too. That's okay. But I need to see something that you actually derived, all right? Now, what I want to do is give you Heron's formula. Heron's formula is amazing, at least in the sense that it is a surprise. So let's look at Heron's formula. Now, when you think about it, and I'm going to just kind of summarize some things here. This first, we need a definition. Define the semi-perimeter. Now, if you look in a textbook on classical Euclidean geometry, there are all kinds of definitions. Geometry is filled with terms. I mean, filled with terms, and it's extremely taxing. Geometry, geometry is like number theory. It's like, man, you think you know a lot, then you study number theory and Euclidean geometry, and you get humbled really fast. I love to read number theory when I'm doing my research and Euclidean geometry to learn new ways to think about things. And again, a lot of them are academic exercises, but if you're going to be an architect one day, the more geometry you know, the better. And the more number theory you know, the better, because you need to understand ratios. So when we talk about semi-perimeter, it's going to be S, and we're going to think about our generic triangle. So let's just draw a generic triangle. And we've got C, A, lowercase a, B, and lowercase b. The semi-perimeter is where we're going to sum the lengths of all the sides and divide by 2. Right there. That's the semi-perimeter. Now, why do things get defined? Well, when mathematicians work on things and they see a particular quantity coming up over and over, they say, okay, we're going to make a definition. Basically, because what is important about moving things forward? Necessity, right? The phrase necessity is the mother of invention. Absolutely. What do we have to do when the COVID hit? Well, we got to change the way we do things. And that pushes us to investigate other ways of doing things that we normally do a certain way. when we don't have all these restrictions. So mathematicians do the same way. Maybe it's not because of a pandemic, but they work on a problem and they see a recurring number. Then they make a definition. Now, what happens here is that if we want to find the area of this triangle, we can use what is called Heron's formula. So we'll say let A equal area of triangle. So if we define the semi-perimeter, then, and this is going to be extremely interesting to you, A will now be the principal square root, I'll draw the radical this time, of S times S minus A. So we're going to get a product of 4 terms, and when we square root it, that'll give a squared area. S minus B and S minus C. Now, this is a major, major result in geometry, and it's truly a departure from what we normally think. I mean, if you consider this, this is not something that probably is so mind-blowing. You think when you do the Euclidean geometry in high school, you have 1/2 base times height. But the height is kind of one of those nebulous things unless you have some given value of the height or you have some trigonometric relationship that we know of, then you don't have any way of determining that. So this actually goes to the next level and just says, okay, we'll just consider the lengths of the sides of the triangle. And if they're combined in this fashion, we get the area of the triangle. So what I wanted to do was just show you a little calculation here and show you the use of this. And then if we have some time, I'll go over the justification. These problems are very important, but they're a little bit different. And I want you to be able to use these new formulas computationally. That's why I did the 2 examples of the law of cosines, because it's a little bit more challenging than the law of sines, clearly. So here's an example of this. And here's just a figure that's composed of 2 triangles. Excuse me. So we actually get triangles that are congruent. So in this case, we have 2 triangles. We have 5. All of these distances are known, and they're congruent. So basically, our figure is composed of these 2 interlocking triangles. So the problem is here, compute area. Compute the area. Now, if you notice here, we've got 2 interlocking triangles, so to speak, and we're only given the lengths of the sides. And if we notice here, they're both congruent. So we can say, okay, if we want the area, we'll just call this 1. So we'll say, in this particular case, area will equal 2 times, and we'll just say triangle 1 area. Triangle 1 area. So that's going to be our formula that we're going to use right there. And these, of course, are congruent. So if we can find the area of triangle 1, then we've got the area of triangle 2, and we just double it. Okay. And now we're thinking we're just given the sides of the triangle, their length, so we can now apply Heron's formula. So let's go ahead and do the computation. So we're going to apply Heron's formula. So I want to give you some uses of this. Heron's formula. So the first thing we want to do is compute the semi-perimeter. So write all this down. A equals 5. And of course, it doesn't matter how you notate these. Any order you like, it doesn't matter what you call A, B, or C. So we're going to say A equals 5, B equals 5, and we're going to say C equals 2 right there. So if you like, you can just say A, B, C. And now we can compute the semi-perimeter. So this is A plus B plus C divided by 2. So it does feel like we're back in geometry class. 5 plus 5 plus 2. In this case, divided by 2. So this is 12. So the numbers are nice here. Don't always count on nice numbers. So we get a semi-perimeter of 6. Okay. So if you don't get a pretty number, it's a fraction, 1/2, a denominator of 2. That's okay. It's no big deal. It doesn't mean the end of the world. This just happened to turn out to be a nice number. So now we can now look at all of these constructs. So we've got S. So let's look at S minus A, which is going to be, in this case, 6 minus 5. That's 1. S minus B is 6 minus 5. Well, luxury of nice numbers. That's 1. S minus C is going to be 6 minus 2, which is 4. So we have all the numbers here that we need. So now this implies that the area, we're going to use our formula, area will be 2 times the area of the triangle. So this is where we apply Heron's formula. I'll use the brackets with the 1/2. So now we have what? Go up here to this formula. S is 6. And then we have S minus A, which is 1. S minus B, which is 1. And then S minus C, which is 4 to the 1/2. So of course, this gives us 2. We have the square root. And of course, this is just a 24. So this is 4 times 6, right? So let's just extract the square root of 4, which is 2. So this gives us 2 times 2 times the square root of 6, or 4 root 6. So this problem with Heron's formula is very simple. Now, of course, the idea that we could use other techniques is certainly on the table. But if you have a triangle area formula that utilizes the lengths of the sides and that's all you're given, then why not? Now, of course, if you don't get a beautiful number or the numbers are kind of untoward, that's all right. You can always get an exact calculation here. So now what's interesting is that as you use certain triangle theorems like law of sines and law of cosines, you can get, like we see with the formulas and all that. And so that requires more writing, clearly. But what we can see is, at least with these new ideas, we have a way to focus on working with triangles that's algebraic and analytic to the point that we can combine the geometry with the algebra, combine the geometry with the number theory, and get some really nice results. Now, if we have time at a later lecture, I'll actually go over this proof. I've written out the proof, and it's not difficult. It's just using a lot of algebra. And if I have time to go over it, I will. But I've got to talk about some other things. So what I might do is just end up posting these so you can go through it. And of course, the proof of the law of cosines is very straightforward too, not difficult. But the application of these theorems more complicated. So I needed to do some examples. So I will say something about those. Now, I want to go ahead and look at some just basic identities. That is, at this point, when we start chapter 7, all we basically have are the identities that we've already introduced here with our study of trigonometry. So we might say basic identity proofs. Now, when we think about a basic identity, we think about something that we can actually prove with the identities that we already know. So to prove an identity, you use identities, and that's not circular. That's just, those are like the raw materials that we have. Now, the only thing that I promised you that we haven't actually talked about are the co-function identities. Remember, we have these beautiful identities from the inverse trig functions. We have inverse cosine of x plus inverse sine of x equals pi over 2. And these actually are equivalent to the co-function identities. We have inverse tangent of x plus inverse cotangent of x equals pi over 2. We have inverse secant. Remember, we proved that one. We proved that one last week. Inverse secant plus inverse cosecant is pi over 2. Now, these proofs were not overly difficult, but we had to start with an equation that was complementary, so to speak, with the way we defined the inverse trig function. So we were actually writing down something that existed, and that made the proof a little bit more complicated. That is, we have to make sure that we respect the range and domain of the inverse trig functions. Now, what does this give us? This gives us the co-function. So we can say, if you like, sine of pi over 2 minus x equals cosine x. Sine, cosine. Likewise, cosine of pi over 2 minus x equals sine. So you're thinking, oh, okay, so we can actually work these problems backwards, because remember, to prove this, we started with something like this. So we're just working the theorem backwards. So that's why I did these. And now it's like, okay, we think about taking the argument in reverse and getting the co-function identities. Now, of course, you can think about these in terms of sides of triangles, but we've already talked about this, so I'm going to use it. So now tangent of pi over 2 minus x will now be cotangent of x. Likewise, cotangent of pi over 2 minus x equals tangent of x. And then lastly, secant of pi over 2 minus x equals cosecant of x. And then cosecant of pi over 2 minus x equals secant x. So these are what we call the co-function identities. And maybe now it makes sense why the terminology is the way it is. I'm sure people thought about this for a long time. Sine, cosine, cofunctions, tangent, cotangent, cofunctions, secant, cosecant. So again, these will be very useful when you do the calculus of the inverse trig functions to see that the derivatives differ by a negative sign. And then, of course, this is just more of an interesting formula that's going to have a segue to the addition and subtraction formulas for sine and cosine. So once we actually prove those, you can think of these proofs as being substantiated using an addition and subtraction formula that we're going to see in the next section. So the idea is that we're seeing that everything's interrelated, and we prove things based on what we know at the time. But then as we move to more identities, we can see how they're basically all related to cosine squared plus sine squared equals 1. That's where it all started, ladies and gentlemen, with the unit circle. And so as we evolve, new mathematics, be it in calculus or analysis or whatever, it must be that mathematics is consistent to what's already on the table. So that's why calculus is so nice when you get to infinite series and you think about expressing cosine and sine as an infinite series. You see it has all the attributes of the even function cosine and the odd function sine. It would have to. But see, that's the beauty of the mathematics. That's why I keep saying we study something and then we continue studying it. And then you might explain to someone, they'll say, well, You just keep doing the same thing over and over. And you might say yes to that, but we take it to a higher level. You know, maybe you're doing the same kind of computer programs, but you're taking your algorithms to a higher level to be able to do more complicated problems. And then you move it up again. That's all we do in education. Let's face it. You know, we reinvent ourselves with the same material and then add a few bells and whistles and pretty much end up doing the same thing, but we get more and more and more expert at it. And that's what's important. So now with these new co-function identities, again, these are just useful, maybe not the most illuminating thing we've ever done. I just want to do a couple of exercises where we validate an equation that is true for all values of the variables for which it is defined. So here's some examples. So let's just start with something easy. So we want to say prove that 1 divided by 1 minus sine squared y equals 1 plus tangent squared y. Now, when you look at something like this and you think about, you know, what's going on here, you can stare at it and say, well, that's simple, Professor Ron. Well, maybe it is simple. Not all identities are going to be difficult. But when we do a proof, and this is the notation in the text, which I actually like, you can start with either side. But usually what students will do is start with the side that seems to have more interesting algebra, in the sense that maybe it's a little bit more complicated. So you take the more complicated expression, simplify it to produce the more simple equation or this more simple expression. So that's really a rule of thumb. Not required, but maybe the best way to do it when you're working something and you want to get, you know, more efficiency into the mix. So we'll say left-hand side, LHS, is 1 divided by 1 minus sine squared. Okay, well, that's the fundamental identity right there. 1 minus sine squared is just cosine squared. That's the fundamental identity. So Pythagorean. So when you're verifying an identity, you can use any algebra you want, algebra, common denominators, factoring, identities that you already know. So everything's on the table and there's no unique way to do it. You might say, well, I took fewer steps. And you say, well, I still verified. So it doesn't matter. Doesn't matter. If you take longer, good for you. Maybe you learn more in the process. Now we look at this and say, well, this is just the reciprocal of cosine squared, which is secant squared. So this is secant squared. But now this is one of our Pythagorean identities. Secant squared equals 1 plus tangent squared. That's the Pythagorean identity, which is the right-hand side. So remember the fundamental identity, we just use y's. Since I've used y's here, use any letter you like, it doesn't matter. These are true for all real numbers. And then of course we have what? 1 plus tangent squared, where it's defined, of course, is secant squared. And then 1 plus cotangent squared is cosecant squared. These get used all of the time. These are really well-used identities because they're all equivalent to the fundamental identity, which is the equation of the unit circle. When I say fundamental, the basic idea that from which everything evolves. When you say the fundamental theorem of calculus, when you say fundamental, it is the bedrock of how you do calculus. That's why it's called fundamental. The fundamental theorem of algebra. All complex polynomials of at least degree 1 have at least one complex zero. That defines how you work with algebra throughout the study of algebra. It is what we call basic. We call it fundamental. Okay, so the idea here is that you can write down more, but the result will be the same. You use identities that you know to push the problem forward. Now, one interesting example here, you'll like this, and this is going to be something we prove later. This is something that you use when you talk about the Weierstrass substitution in Calculus 2. It's basically the half angle formula for tangent. But right now we'll just call it a different name. And this introduces a technique which I've talked about before. That is, this expression here is the tangent of x over 2. It's the half angle formula for tangent. We'll prove that. But when you get to calculus 2, this type of substitution will allow you to integrate rational expressions of sine and cosine that cannot be done by simpler methods. Lots of times you can do a conjugate method, you can do some trickery and make the problem simple and don't have to take out the larger artillery. But when they don't work, you have to try something else. And so students don't particularly like it, but it reduces the problem to something doable. Okay, so when you look at this and you think, how do I do this? Well, this is where the conjugate method is very useful because you see these Pythagorean identities. As long as the coefficients are maintained here, these work really nice. The only problem is when you get awkward coefficients and you end up with elliptic integral integrands that are difficult. But at least for now, we're going to basically see that these are the linchpin, so to speak. These are the fundamental equations that will allow us to rewrite this to make it into that. So let's do a proof and I'll show you the conjugate method. So we say the left-hand side, again, you can start with either, it really won't matter in this case, 1 minus cosine x. What's an identity? An identity is an equation that is true for all values of the variables for which it is defined. You should know that. Now, the conjugate method is basically like a complex conjugate. You just reverse the sign that combines the two numbers. That is here, this is a plus, so we're going to reverse it to, this is a minus, so we're going to reverse it to plus, so we can introduce the Pythagorean identities up here. So we're going to multiply and divide by the conjugate. I'll put this in another color. You don't have to do it, but just making an impact. Something like that, okay? So if you look at this, you're thinking, okay, well, that's good because I do need a 1 plus cosine in the denominator here if I'm going to morph this into that. So maybe that's not a bad idea. So let's see what we get. And it's really simple. This is called the conjugate method, just like we say complex conjugate. Conjugate method, very useful method, especially when you're working with Pythagorean expressions, differences of two squares, things like that. So in this case, we just get what? We get the 1 minus the cosine squared because the outer and the inner absorb. That's a difference of two squares. So this is 1 minus cosine squared. And then, of course, downstairs, we have sine x times 1 plus cosine x. The thing is that as you look at where you need to go, you're thinking, I'm not going to go ahead and multiply this because I'm actually going to need that here. So maybe that's a good thing that I leave it alone for now. And hopefully I'm going to absorb the sine because that's really in the way. And of course we get that because now we go to the Pythagorean identity and we're back to square root 1. 1 minus cosine squared is just sine squared. So this is really simple once you do the conjugate method. And so what I will say is that when you use the substitution technique in Cal 2, we more so focus on this expression than we do this one, just historically. So now we can see that one of the signs will absorb here. So this one of these signs will absorb that sign, and this leaves us with sine x. If you like, you can just write this as sine x times sine x. And so this absorbs with the one here and leaves us a sine x, 1 plus cosine x. So this wasn't very difficult, but you can see that the two expressions are identical where they are defined. What's an identity? an equation that is true for all values of the variables for which it is defined. And if there's more than one variable, we need to say variables, but here we just have one. So when we look at this, this is defined for all real numbers y. That's very useful, okay? And identities are extremely important, just like the logarithm identities, okay? We have to abide by the domains of the logarithm, of course, and that's one thing we have to respect, as we've seen with the inverse trig functions. But boom, right here, identities, right? As long as x lives between what, -1 and 1 here, that's important. Here we can get all real numbers because inverse tangent and inverse cotangent are defined for all real numbers. And here, of course, we've got what, -infinity and -1, union 1 to infinity. So again, we have to respect the domains that we define when we actually make these functions one-to-one. And so we can't forget that. What's so nice about these is they're much more user-friendly. It's just when you go up to here, they're less user-friendly because, again, the domains are more restricted. Okay, so not so hard, but interesting. Now what I want to do, again, when you do section 1, you just basically look at ways that you can combine trig functions using algebra, basic algebra like we've been doing, and verify identities using identities that you already know. So let's try another one. Again, this is easy. I thought you might enjoy this. This is kind of fun. This is called mathematical entertainment. So now we have, and I'm using Y's. I don't know, I just change it up. I don't want to use alphas right now. I use the easy letters. So we have tangent Y times sine Y divided by tangent Y. We've used this construct before, especially when we were dealing with the triangles. Sine Y. This should be equal to tangent Y minus sine Y divided by the product of tangent Y sine Y. Now, of course, you know, you're thinking, well, I could just deal with the equation as it is and show that 1 equals 1 or something. You know, true, that would, you know, you're thinking, well, if they're equivalent, I can just cross multiply or whatever. Right, but technically, we have to start with one side and morph it into the other. That is the technical proof, okay? And that's important. And so when you verify an identity, you have to algebraically show that one side is actually equivalent to the other. So that's the technique that we use. And I know you want to do more, but don't do it because we want to, again, when you're doing a problem where you're just working on your own, you can use any methods you like if it gets you to the next step. But for the proofs of the identities, we want to start with one side and transform it into the other. So let's do a proof here. Now, what I'm going to use is something I've already talked about when we were dealing with the triangles. And I will write that. Let me just write this down. The left-hand side is tangent Y times sine Y. And then we have tangent Y plus sine Y. Now, if you look, and this is something we've done many times, notice tangent Y, here's a little sidebar, is just sine Y over cosine Y, okay? So this implies that tangent Y times cosine Y is just sine Y. Now, a lot of students will say, do I just convert everything to sine and cosine and keep my fingers crossed and make it easier? Well, sometimes that's fine and there's no problem with that, but it's not always required. You just want to make the problem flow from one step to the next. So if we look at this and think, okay, well, where do we need to head with this? We're thinking that we've got to introduce some kind of square somewhere so that we can get a Pythagorean identity to basically end up with a minus in the numerator. So we want to flip everything. So what we're going to do, and this is just a way of looking at it, we want to use this construct. So if we multiply by cosine 1 over cosine Y, this is going to give us a square in the numerator, which is what we need. So I'm going to use this key right here. So I'm going to multiply in both cases by cosine Y. Cosine Y divided by cosine y. So this is basically an algebraic technique where we multiply by one, a convenient one, as Professor Ron often says. So this is the convenient one. Again, I'm using this construct here so I can get a sine squared in the numerator. So this is basically using what you know. So now we say, okay, well, that's going to be a sine y times a sine y. So when I multiply the cosine times the tangent, I get the sine as I've written here. So I'm using this construction. And then downstairs, again, we can do the same thing. Notice the cosine times the tangent, again, is sine. So we get sine y. And then, of course, we get cosine times sine, and that doesn't reduce. So we just say sine y times cosine y. So again, I'm using this over and over right here, just making that illusion. So to do this, I'm using this identity here. Even though it's very simple, it's actually very important. Now notice we have sine squared. And one thing that we can see with this construct is we've got in the denominator a sine in both of these terms here, and then we're thinking, well, can we get something to simplify this? That is, are we going to be able to absorb a 1 plus a cosine y? Well, we certainly are, because we're going to factor that. So let's go ahead and factor sine y, 1 plus cosine y. I wanted to do this one last because it's a little trickier. Now, this is Pythagorean, so we can use the Pythagorean identity. So this is 1 minus cosine squared. Again, we want to absorb that, and of course we can do that when we factor it. Now, nothing about what I'm doing is unique. It's just simply the way I'm looking at it. It's not unique. None of the proofs that we do are unique when it comes to this. You can try anything you like. So we have 1 minus cosine y times 1. Oh, that's good. We got the minus up there, so that's going to help us out, plus cosine y. And so we have sine y, 1 plus cosine y. So now we can see these will absorb. So this will give us 1 minus cosine y divided by sine y. Now this is the easy part. We're thinking, okay, how do we get that? Well, we just multiply and divide by tangent, because I need tangent times sine. I've got the sine. So if I multiply by tangent up here, I can basically use the same construct I have here. So that once we get to this point, it's easy. So we just say tan y, tan y. So of course now tangent times 1 is just tangent. And now, of course, the cosine will absorb it in this particular case and just leave us with the sine, just using this construct. So sine. And then, of course, downstairs, we just have sine. Well, I'll write the tangent first, right there. So again, notice when we multiply here, the cosine absorbs, and we're left with the sine. So we're kind of taking this backwards. So we're basically saying in this case, when we multiply here by the cosine, in this particular case, we get the sine just like we've used here. So this is the same. I don't really have anything new to write. That's where we started with tangent. So we get this construct again. And then, of course, this is the what? Right-hand side. Now, this is certainly not a unique proof. It's certainly a way of looking at the proof. And so what I want to say, there are actually three huge techniques: the conjugate method to utilize Pythagorean identities. And then, of course, the convenient one to utilize identities to morph things very simply by making some reference like this. And then, of course, just basic algebra. Basic algebraic identities, common denominators, factoring identities, difference of two squares. So you can look at the actual identity and step back and say, okay, well, if I need to take this into this, I've got to be able to simplify it some way. And then you're thinking, if I've got to somehow get a product here, then I'm going to have some way to get rid of a sum. And how do you get rid of sums? Well, you get rid of them with Pythagorean identities that you factor because they're differences of two squares. So this particular type of problem will tend to be more complicated, even though once you do it several times, you'll do this without thinking about it. So when you take calculus, it'll be the same way. These types of identities we're doing here, you're going to do when you work with derivatives, when you work with integrals, because you're going to rewrite things so you're making them more user-friendly. So what do I mean by that? So let's look at one. Here's a construct that I really like about Dr. Stewart's treatment. And it's basically how I've always taught things myself when I just make up my own notes and things, which is basically what I do. I just like having a homework system that I think is fairly decent. With all these trig things, you're thinking, how is all these trig identities going to help us do calculus? Well, here's an example. Here's an example of what we call trigonometric substitution. And for short, you're going to call it trig substitution. And these are all based on Pythagorean identities, which I've said a million times, which I've written down maybe 500,000 times. So if we look at the following expression, this is Pythagorean in the sense that it reminds you of a right triangle. So we have 4 plus x squared. Now, when you look at the square root of 4 plus x squared, you're thinking, well, that looks like the hypotenuse of a right triangle. So here's what's going on in this case. Let's just kind of work backwards and say, you know what, Professor Ron, I love triangles, because triangles, not law of sines and law of cosines, that gets kind of tedious at times. I mean, just keeping track of everything, but just your basic right triangles, so simple and so easy. So here's something that I want you to notice here. If you look at this, you can think, if I square x, I get x squared. If I square 2, I get what? 4. So you're thinking, well, let me just draw a right triangle here. And I'm going to put theta here. Remember, ladies and gentlemen, you have to know the unit circle and how the ratios of the sides are related to the trig functions. And some of you still don't know this, and that's unfortunate. So you need to get busy and it's just basic, okay? Go back to the fundamentals. So now we're thinking, okay, we might have an x here and a 2 here. So x squared plus 2 squared would be the square root of 4 plus x squared, okay? So this triangle matches that radical right there. It's Pythagorean. And then you're thinking, oh, I see. If I look at this and say, how does this relate to a trig function? Well, this is Pythagorean. And if I can replace x with a trig function that will simplify this to one square term, we'd be banking really good. So here's what we're going to do. We're going to say this implies, or this is equivalent to the following: tangent. This is how if we started with this, we'd get this, but now we look at that and go backwards. We'll say tangent of theta equals x over 2. So tangent of theta is opposite over adjacent. So this defines this triangle. For instance, if you start with this, you get that. We've already been doing that many times. So the key here is you're thinking, why do we do this in calculus? Well, there's other reasons besides just the fact that this is Pythagorean. The other reason is that the calculus is supported by this, and that's what's important. So you're thinking, is it going to be easier to change this up with the trig function so that if we have to integrate it, that it would be easier? And the answer is yes. So here's the deal. Why do we do this? Why? Well, here's the reason. That is, when you get to calculus, you're going to integrate this expression, dx x squared square root 4 plus x squared. That's what you're actually going to anti-differentiate. And then of course you could have limits of integration. So the key here is that why do I teach you trigonometry? So when you get to this, you know how to do it. Okay, so the key is, and in the WebAssign, here's what they say. They say, now take this, they say let x equal cross multiply 2 times tangent theta. That's the trigonometric substitution right there. Now, something you're going to learn in calculus is that the differential will now be 2 times secant squared theta d theta. And that's something you're going to learn in calculus. So that's going to come later. So the key here is that we're going to transform all of this into a bunch of trig expressions, which we can more simply anti-differentiate. So that's why I like the trig and why I kind of try to push you in the direction that you're going to eventually have to go. So now let's go ahead and do the substitution and see what we get. So we'll have 1, and then of course x squared now will be 2 tangent theta squared, 2 tangent theta squared. And then let's go ahead and put in the radical. Of course, we usually do this on the side, but I'll just do it all together. We'll have 4 plus, now if we squared it here, let's just go ahead and write it out. This is going to be 4 tangent squared. So now, of course, we can factor the 4. So this gives us 4 tangent squared theta. And then I'll do brackets now. So we have 4, and this will be 1 plus tangent squared. That's our friend. That's our Pythagorean identity to the 1/2. So now, of course, the square root of 4 is 2. So we'll have a 2 times a 4. That'll be an 8. And then we have 1 plus tangent squared theta to the 1/2. Well, that's just the absolute value of secant. The thing is that this 1 plus tangent squared is secant squared. I'll go ahead and write this out. You won't do all these steps because you'll be able to write this out in a theoretical way where you don't have to put on all these steps and when you get to calculus. But for right now, you need to see them. So this will be, and I'm going to go ahead and use the radical symbol now. This will be the square root of secant squared right there. So now the square root of secant squared is just the absolute value of secant. Now, when you look at this, we're thinking, okay, if we look at what we have here, let's write an equivalent expression. Tangent, or theta, if we apply inverse tangent, is the inverse tangent of x over 2. We've done that. We've done that a million times. And we know that the inverse tangent lives between what? Negative pi over 2 and pi over 2. Again, we know the range of the inverse tangent. But for these values of theta, the cosine is positive, non-negative. So the secant is non-negative. So in this case, the absolute values can be removed. So we get 1, 8 tangent squared secant theta. So the idea is that we've reduced this part to this, and you're thinking that's an improvement? Well, somewhat. The key is this. Looking at, there'll be some times when you can actually use another technique to avoid the trigonometric substitution. That's called integration by parts, or possibly a miscellaneous substitution. There are often many methods to compute antiderivatives. But notice now, just using the fact that we have basic trig identities to get us from here to here, we can now say, well, if this is the actual dx, what is this going to end up being? So now this implies, and we'll use some more trig identities, that we end up with the integral dx. So we get 2 secant squared theta d theta. D theta is just a right now just an object. Don't worry about what it means. And then we have 8 tangent squared. Oh, I left out my theta, sorry. Theta, secant theta. Now let's just reduce this. One of the secants in here will absorb. So we get 2/4, which is 1/4. And we get secant theta, d theta. And downstairs, we just get tangent squared theta. Now let's just kind of look at this and see, what is this going to give us? This is where we can use our trigonometric identities. So let's do this. Tangent squared is what? That's just what? Sine squared over cosine squared. So this will be 1/4. And sine squared over cosine squared reversed will be cosine squared theta over sine squared. And now secant is 1/cosine. And of course, we'll just stick on our d theta. So all we're doing is basic trig identities here. Nothing, no calculus. I'm just writing the calculus symbols because that's what you're going to do in Cal 2 and Cal 1. And notice the cosines absorb, at least one of them. So we get cosine theta, and we get 2 copies of sine theta. I'm going to write them out this way. So you're seeing that all of this manipulation here is pre-calculus. Now look, we can break this into 2 pieces. We've got 1/4. The 1/4 will be able to factor later. You're going to learn about that. This will be, we'll have what? 1/sine theta times cosine theta over sine theta, d theta. Now what's 1/sine theta? That's cosecant. And what's cosine over sine? That's cotangent. And this particular integral you can do very easily. So notice we haven't done anything but trig identities. That is, I gave you some justification as to why you would actually use this substitution. You're going to get more of this in calculus. But you can see that this is related to that triangle. This triangle is related to that Pythagorean expression right there as the hypotenuse of this right triangle. And the reason this particular substitution not only works is because it complements what we have here in terms of the algebra, but also complements the calculus. And so then we just substitute and we transform this into this. And then we say, okay, well, once we learn the calculus, we know what the dx is. And so we substitute that and then just do pre-calculus and end up with something like that. Again, what you're going to learn is that the derivative with respect to x, well, let me just go ahead and use theta since we've got thetas running around, of cosecant theta is actually the negative of cosecant theta cotangent theta. You're going to learn that in Cal 1. And so what you're going to see using the fundamental theorem is that this will give you the antiderivative of this. That'll be what you're going to learn in calculus. But here's what's important, ladies and gentlemen. If we look at this, we think, okay, this is a little bit complicated, but if we use a trig substitution, we can formulate this in terms of trig expressions, then use, again, pre-cal, 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 pre-cal. I haven't used any calculus yet. And then at this point, I use calculus right there. Pre-cal, 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 pre-cal. Then to do this, to finish the problem, calculus. So we use that much calculus and this much pre-cal. So when you take calculus, if you don't know pre-cal, you can't do calculus. And you all think that I'm a tyrant. You think that, oh, you're so tough, Professor Ron. Well, ladies and gentlemen, if you can't do this, you cannot do calculus. So you can, you can curse me, you can be mad at me, but I know what you have to do. And I know you want to be a STEM major, and I know that you want to change the world. So people that change the world, ladies and gentlemen, have to pay your dues. You some and some of you, we might have another Bill Gates. Who knows? Who knows what you all are going to be able to invent? I've got students now, two students now working on PhDs. One does computer science, and he's traveled to Europe to show his investigations, and another one at Texas A&M, who's working in biomedical engineering. I mean, it's amazing what you all can do. So what I want to point out here is that, and this is why I wanted to get to this quickly, is that you can see with basic trig, we can actually rewrite expressions using what we call a trig substitution. So all I want you to do is appreciate the pre-cal that we have to do. I put in the other symbols, so when you get to calculus, you'll understand what the symbols are. But the main thing with the basic trigonometry is that now we can at least navigate the fundamental problems. What do we have left to do? Well, what do we have left? We have to do this. We have to say, okay, what are some new identities? We need more identities. We don't know a whole lot about the trig functions. Can we combine them in different ways? That's going to take up some time. And then we're like, when are we going to start solving equations, Professor Ron? We've done the law of sines, but are we going to actually solve some equations? Yes. And that will be the ultimate part. So we're going to take everything we've learned and mash that into techniques to solve trig equations. So you will use trig equations in Calculus 1, Calculus 2, and Calculus 3. So the key is that we're little by little going to give you all the raw materials that you need to do calculus. And so after we finish trig, we'll start talking about conic sections, because those will have an impact on calculus, especially with curve theory. We're going to talk some about sequences and arithmetic sums, geometric sums, math induction, binomial theorem. So we're going to give you all the raw materials you need in order to be successful in calculus. And as I've had former students before, they say, Professor Ron, pre-cal was harder than Cal 1. I said, good. How'd you do in Cal? Oh, I made an A. I said, exactly. That's what I want to hear. So what I'll do on Thursday is do some review problems. What I may do is spend a little bit of time going over some of the proofs that I didn't have time to do this morning. I may say a little bit about that, and then I'll do some review problems. And of course, you'll have your test available on Thursday and Friday. Nice long window, as you normally have, to be able to do your planning. Again, just like in the email announcement and the Blackboard announcement, you'll submit your test work like you've already done. And again, the test work has to support what you're doing. If I have you do a computation, you can't just say, here's the problem, it equals this. You have to fill in all the details. By now, you know what to do. Ask my calculus students. One thing about the online education is that I have to see your work. Just think that you're sitting down in the classroom and I'm sitting at the front of the room smiling at everybody. I mean, we could be doing that with the lockdown browser, but I'm not going to put you through that. So you have to show me your integrity by submitting your work, your test work, and in an honest way. Okay, so that is how we transform the face-to-face classroom into the virtual classroom. And then I give you the option of being able to take the test in a time frame that gives you flexibility and helps to build your success. So again, remember that this is what we have. Follow the rules, be flexible, plan out your week, make sure that you have time to do what you need to do, navigate the water, so to speak. And like I say, on Thursday, I'll do some review problems, and I'll actually talk about some of the things that I didn't have time to do today. And I will, of course, send out some email invitations for our conference hours today and tomorrow. So if I see you there, that'll be great. If not, I look forward to seeing you all on Thursday. And so enjoy the nice weather. Be safe. Be safe as you go outside. Don't take any chances. I know you all are young and you're 5 years old, but still, I want you to be safe. So take care. Have a great day.